most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of 36 seconds and 10 to the power of 32 seconds, space expanded exponentially, growing much larger in size. After this period, space continued to expand, but at a much slower rate, eventually leading to the universe we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. However, for a few physicists, this premier theory doesn't paint an accurate picture of the evolution of our universe. They suggest that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when a shrinking universe reversed course and began to grow. According to their theory, the universe could bounce again. Today's expansion could be followed by collapse in the far future, followed by another bounce. Some physicists have suggested that this bouncing could be infinite, which, of course, counters the way most cosmologists see it, where everything started with the Big Bang. But what's noteworthy here is that this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding a bit of tension, the James Webb telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even then, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in four anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem that it has sometimes been called a crisis for cosmology. Third, the two hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense, since we believe that the universe should have started out uniform on average. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby stars. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats, and the hot Big Bang starts. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again, and again, and again. The process is relentless. But once the Big Bang begins, all of that changes as the expanding universe immediately slows down. Once the first moment of expansion elapses, probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within space-time dominating its volume. These regions where hot Big Bangs occur will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view in the standard inflationary picture. Because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. All of these raise a question: if the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce or something else entirely? Join us as we dig deep into one of the thornier questions in physics. The idea that the universe had a beginning, or a day without a yesterday as it was originally known, goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that described our early universe. Although many laypersons, and even a minority of professionals, still cling to the idea that the Big Bang means the very beginning of it all, that definition is outdated. The Big Bang is not the birth of time and space as we know it today in 2023. In fact, there's a ton of evidence that points to a non-singular origin of our universe. We never achieved those arbitrarily high temperatures, there's a cutoff instead. Our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time by about 1 part in 30,000 on average. As the universe inflated, expanding in a rapid, relentless fashion, those fluctuations got stretched to larger scales, while new small-scale fluctuations were created atop them. This superposition of fluctuations on small scales atop intermediate scales atop large scales atop superhorizon scales is one of the defining predictive features of cosmic inflation. This continued as long as inflation went on, but inflation would come to an end randomly and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang before that region disappeared entirely from view in an initially relatively small region, perhaps no bigger than a human-sized hamster ball, but perhaps much larger. The energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of 33 seconds or so, a brief amount of time, but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise from just a few degrees above absolute zero to perhaps around 20 Kelvin over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation, with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions.